Okay, our last talk for the afternoon is going to be given by Dzmitry Dudko. Title of the talk is MLC along the real line.
Yeah. Thank you. It's a pleasure. I'd like to talk about the problem of local connectivity of the Mandelbrot set and related questions, mostly restricted to the real line. The first page contains a very brief summary of activities before 2000. Well, it was DoD and Hubbard who realized that the Mandelbrot set is an interesting mass object, and they put forward the MLC conjecture in the 80s, I guess at the end of the 80s. Well, they also developed a foundational theory of the Mandelbrot set. Early 80s? Okay, sorry, yeah, feel free to correct me. Yeah, well, Jean-Christophe Yacoz proved the MLC conjecture for all non-infinitely renormalizable maps, I guess in the beginning of 90s. Right, yeah. Well, shortly afterwards, it was realized that the opposite case is fundamentally different. And in particular, the opposite case is related to the universality phenomenon discovered by Feigenbaum and by Collet and Stresser. Well, in the middle of 70s, Feigenbaum decided to play with the calculator and compute the speed with which parabolic points approach the limiting bifurcation. So he computed the number. This was the number. And then he decided to do the same for the sine family, and turns out that the number is the same. Well, and he had some backgrounds in physics where renormalization was already discovered. Therefore, he conjectured that this is a universal phenomenon, and there should be some renormalization hyperbolic operator explaining the picture. Well, nowadays we have good pictures, and this property can be stated as universality or scale invariance of the whole Mandelbrot set under a linear expanding map with an arrow term. Well, independently, Collet and Stresser discovered the dynamical counterpart of this universality. In the 80s, Lanford gave a computer-assisted proof in the case of period 2 with a transversality argument added by Ekman and Witwer. Roughly, Lanford approximately computed the limiting fixed point and then checked by computer that indeed we have hyperbolicity. The mathematical theory was developed later, and it took several independent papers, so by Sullivan, McMullen, and Lubitsch. Dennis constructed a renormalization fixed point and showed that there is a weak convergence towards the limit. Kurt proved that the convergence is in fact exponential. Namely, there is a hyperbolicity within the hybrid class. And Misha constructed the unstable direction and obtained the parameter scaling. So this approach is quite soft, and it's applicable for other combinatorics. Well, the theory was completed by establishing real rigidity for quadratic maps, which is equivalent to hyperbolicity in the real family, real rigidity, real hyperbolicity, and by establishing regular and stochastic dichotomy. So let me make a few comments about this dichotomy. Well, an important step in this dichotomy was to show that the real area of infinitely renormalizable polynomials is 0, and very roughly Well, this is the area of the non-escaping set. Of the renormalization map restricted to the real parameters. And this area is zero because, well, if we have an expanding system, then we should expect that the non-escaping set is a Cantor-like set with zero area. Well, expanding in this style. Well, the opposite case, the non-renormalizable case, required different approach. So, and it was based on the theory of generalized quadratic-like maps. So these are maps that have several domains inside, so that all map with degree 1 except 1. So these maps naturally appear as a first return map to a puzzle. Well, let me also stress that the development of all this theory required an important ingredient, namely some sort of compactness as we go deep into the scale. For real maps, there were a priori bounds established by Dennis. So real maps have an invariant line, the real line, which helps a lot. For complex maps, such luxury is not available. So in particular, the MLC question was open for real maps. So the MLC question is a question about how real polynomials sit in the complex plane. And they do require, well, at least it seems so, a priori bounds for all maps that are equivalent to real maps, combinatorially equivalent. Well, a very fruitful approach to establish bounds in the complex case is the near-degenerate regime. The fundamental idea is that surfaces degenerate in a very specific way along thin annuli and white rectangles. So we have seen some of such degenerations in the previous talk. And this idea was central in the work of Bill Thurston, who established many results that give a control about the boundary behavior. And as an example, if we consider the Thurston iteration for post-critically finite maps, so this iteration converges to a fixed point if and only if the map is realizable as a rational map. Well, then such iteration diverges. If such iteration diverges, then the divergence is along an invariant multicurve. So the divergence will be in the modular space, and such divergence is controlled by the Thurston matrix. And what's important in the near-degenerate regime, this Grotch inequality can be effectively replaced by equality. So roughly speaking, we can forget about small spheres. They're very small. And our map becomes almost linear. And this means that we can diverge to infinity if and only if we have an abstraction. Any comment?
No, I was going to say what you just said.
Okay, good. Yeah, that's essentially how we prove the Thurston theorem. So there are soft arguments involving Teichmüller theory about contraction of the map and many other interesting moments. But then at some point we need to say something, and the way how we do it is by reversing the Grotch inequality.
Well, maybe helpful to comment that thin annuli means fat annuli. It may be helpful for some to realize that thin annuli means fat annuli. Right?
Okay, yeah.
Yeah.
Special annuli, right? Yeah.
Large modulus. I mean, this.
Yeah, large
If you're
modulus.
not used to thinking thin equals fat, then you get confused.
Yeah. Right. So in what follows, I'd like to keep this example in mind. So this is my last slide. So let's go to renormalization. And it was Jeremy who introduced these ideas to the renormalization theory. And in particular, he established bounds for primitive bounded combinatorics. So in particular, this implies MLC for the corresponding parameters. For example, for the airplane tuned with the airplane and so on. Well, bounded means that periods are bounded by some number. And the idea is to look at the degeneration of the Riemann surface obtained. Yeah, I'm going to introduce notation soon. So at this Riemann surface, so let's write more notations. So we start with a quadratic polynomial, then we start to renormalize it. So we obtain a map from UN towards Vn. So let's draw it. So this is Fn plus 1. So let's say that Fn plus 1 is the nth Pn iteration of Fn. And Fn plus 1, in fact, sits in the dynamical plane of Fn. So this is a small Julia set. And the bigger Julia set continues. Well, and our goal is establish bounds on the modulus. So we want that the modulus of Fn, which is the modulus of the fundamental annulus, for example, is greater or equal than epsilon. Or it will be slightly more convenient to invert this parameter. So we would like that the width of the map is less or equal than k. So these are bounds that we want, and the quantifier is that there is k, such that for every n, this holds. And these bounds do imply the MLC, well, at least for real combinatorics.
For bounded case, it implies MLC for any combinatorics.
Yeah. Well, it's by degeneration. Well, we know hopefully what is a degeneration for compact surfaces, perhaps with marked points. Well, and if we have a domain inside C minus some other domains, well, then the degeneration will be along white rectangles. But since we are interested, or at least we wanted to display on the picture homotopy types of these white rectangles, it's better to draw it differently. It's more convenient. So let's do a Photoshop. So the convention will be that narrow on a picture means white in reality. So this is how we are going to draw this configuration. Yeah. Well, now if we look at the degeneration of this object, so we have Vn. So we have small Julia sets. Well, then, just like in the Thurston situation, the degeneration happens along an invariant multi-curve. Well, here also the degeneration should happen, and in fact it will happen along an invariant curve. But we know that such maps have invariant objects only like Hubbard tree and spiders. So the generation happens along Hubbard tree or spiders. So the first is called horizontal. The second is vertical. And a key fact is that horizontal degeneration form a substantial path. Question, comment?
Vertical degeneration forms a substantial part.
Vertical, yes, thanks. Yeah. Key fact. Right. Yeah. So red color. So there exists a delta. And just to illustrate the principle, so let's assume that delta is equal to 0. Well, then our configuration will be only of rectangles representing the Hubbard tree. So let me make them smaller. Well, it's just like in the Thurston case, the Thurston matrix controls what's going on. So here we have the positive co-entropy that prevents such picture. So if we take a pre-image, so we obtain this. Well, actually, again, if we ignore small Julia sets, then this should be almost linear map, which is impossible since the co-entropy is zero, is positive. So the entropy on the Hubbard tree is positive.
Are you excluding any of the two cases?
Yeah, primitive. Yeah, and primitive exactly means that entropy is positive. Well, and now as a corollary, let me. So, I mean, if we think carefully, then we can sort of guess and understand kind of what contributes to degeneration on the next level. So we can just see which rectangles contribute to the degeneration of Fn plus 1. And as a corollary, we obtain that the width of Fn is going to be greater or equal than period times delta, well, perhaps some other delta that is compatible with the original delta, times width of Fn plus 1. Well, and if we assume that periods are sufficiently big, depending on delta, for example, by skipping a few renormalization, well, then this would be bigger than the degeneration of Fn plus 1. let's say by 2022. Well, 21 is better. Right. Well, and yeah, of course, everything assuming that we are already in the near degenerate regime. So it just means that once we pass a certain threshold, the degeneration cannot increase anymore. So this implies bounds.
After you photoshopping,
Yeah, let's.
After your photoshopping, I tend to get confused. Large widths are bad. You want small widths.
Well, since we are working from contradiction, the more widths we create, the better for us. Well, this is kind of because we are doing from the contradiction. So the whole idea is that assume something is bad, sort of there is a big width, and we wanted to degenerate a bigger width. And if we can do it, then there would be a contradiction. Yeah. Well, let me just mention that this requires a little bit more explanations. So in particular, Jeremy did develop a formalism of pseudo-quadratic-like renormalization. So let me not go into details. So this is to make this argument precise. And also it's better to apply a covering lemma at certain moment. Developed by Jeremy and Misha. Any other comments, remarks, suggestions?
Yeah, sorry, just to say that, right, if the width for n at level n+1 is big, then the width at level n is bigger.
Yeah.
And then you could just go all the way back to level 0. Yeah.
Yeah. Yeah, as Jeremy says, what was the exact phrase? Yes, something
It's bad now, it was worse earlier.
Yeah. No, yesterday. Okay. Yeah. Okay. Right. But the comparison that I would like to kind of mention is that we clearly can see similar ideas if we oversimplified what's going on. And then in the near degenerate regime, our oversimplification can be justified, usually, sometimes. Yeah.
So this, but I think I remember, so this bad now, worse yesterday only applies in the near degenerate regime. Is that correct?
Yeah, only after we pass through a certain threshold.
So where exactly do you use that you're in the near degenerate regime in this argument?
Well, I mean, all these arguments are up to kind of OB of one that depends on, let's say, the period. So all our inequalities that we write usually contain this type of terms. And then if the width is really high, then we can effectively ignore these terms.
Okay, thank you.
Yeah.
Could you just say what almost linear means?
Well, conformal. So, well,
Okay.
it should be like
Piecewise
A times D.
or-
Well, A times D.
For the whole.
Yeah.
Okay.
For whole rectangles. Well, similar story here that it should be a covering map on rectangles. Sorry, a covering map on annuli. Well, and we know how the modulus changes under a covering map, and we do a naive summation. And the statement is that kind of, again, it's equality up to or big of one depending on something.
Thank you.
Okay, good. So well, a few years later, together with Misha, this result was improved for all combinatorics epsilon away from the main molecule. So for combinatorics or for MI, for small copies, epsilon away from the molecule. Equivalently, co-entropy is positive. And idea is sort of combine in the near degenerate regime this principle with a theory of generalized like renormalization. Where was it? Ah, yeah, it was here. Yeah. So with generalized quadratic-like theory and a rough idea okay, not here. Where did I introduce notations? Was it here? Yeah. No. Yeah, too many. Okay. Right. Not this one. Not this one. Well. Right. Yeah. Okay. Yeah. Kind of a rough idea is that generalized quadratic-like renormalization allows to discuss scales between two consecutive scales in the high type. So using these ideas, if the period is really high, then the degeneration from here to here could be pushed using generalized quadratic-like maps. So that's yeah. Okay. Okay, not this one. Yeah, well. I forgot how the German system works. Yeah. Yeah, right. Well, but kind of important remark is that combination should be done in the near degenerate regime. And in particular, a formalism of pseudo-puzzles was introduced. Okay, good. So yes, this should be free. Well, recently we improved the original Jeremy arguments for bounded types together with Misha, and obtains bounds for all bounded types. Which implies in particular MLC at the classical Feigenbaum parameters. And let me illustrate the idea. So we wanted to use kind of this formula and if this is not applicable, so let's assume that this is not applicable. So assume delta is equal to 0. And I'm going to draw the picture of the Feigenbaum parameter. So this is our map at the nth iteration. So it has the Feigenbaum combinatorics. Small Julia sets of level n+1 they touch. So let's consider small Julia sets of level n+2. There are 4 of them. Well, if this approach works, then there should be an invariant rectangle that connects these two bouquets. And topologically it can happen. So let's consider what happens under the dynamics. So let's take the preimage under, let's say, the 10th power. Well, then, topologically, we more or less know what should happen. So the preimage should behave like this. So let's call it A tilde. And the original rectangle should travel through this A tilde. Well, now I did switch blue into red, but well. So the original rectangle would travel like this.
Do you mean the pre-image travels like that? Or
Well, A tilde is the pre-image, and we just took the original rectangle that connected these two buckets and kind of put it in kind of on top of the A tilde. Sort of, we just combined these two pictures.
okay.
So the original rectangle goes through its pre-image. But they have almost the same width. Well, and this only possible, well, now we need to remember that there are a little bit of arrows. So because without arrows, this is an impossible configuration. But if you remember that we have arrows, then this bit, let's call it L, must be extremely more degenerate. So where M is sufficiently big. And to complete the argument, we need to, it's enough to realize that this L hits small Julia set of the next generations. So L hits preperiodic small Julia sets of level n plus 3. And this means that we can put the degeneration of Fn into the next deeper level with a huge improvement. And this would be a contradiction because of the Teichmüller contraction. So let me write it down. And also how the quantifier works. So we choose sufficiently big M so that it would beat the Teichmüller contraction coming from the straightening map. And then depending on this big M, we choose sufficiently small delta. Well, now if the width of Fn is sufficiently big, well, and And what was written here doesn't work. So if this inequality doesn't work, well then, the width on the next level will be bigger, much bigger. Which is eventually impossible by the Teichmüller contraction coming from the straightening map. Any questions, comments?
This Teichmüller contracting, is that just for bounded type combinatorics, or is it more general?
Right, yeah. So we choose a bounded type combinatorics. Depending on this bounded type combinatorics, we have finitely many small copies. There is a straightening theorem saying that the dilatation in dynamical planes over all the small copies, when we do the straightening, is less or equal than some constant, and this constant will control. So this constant descends to deeper renormalizations.
But it can be applied to unbounded type too, true? So this contraction argument.
With more work, yeah, right.
Well,
Not
just to bound the first iterate and then contraction works for us.
right,
First
yeah,
iterate of
yeah, so if you can bound the first iterate, then it would work. Sort of for finitely many small copies of the Mandelbrot set, well, this is compactness. Yeah. Right.
Can you say again what Teichmüller space you're talking about and what contraction?
Okay, so let me write it down. Well, suppose we have a straightening map QC between two quadratic-like maps. And suppose this map has a renormalization like F2, some iterate. Well, then we can just restrict this QC conjugacy to QC conjugacy on this domain. It doesn't have to be optimal, but it restricts. Yeah, right.
So yeah, so you get bounded exponentially bounded growth of
Right,
moduli,
yeah.
of widths. Yeah.
Yeah. Right, and we,
contraction.
yeah. Roughly speaking, we construct a family of QC conjugates between the second renormalization and the first renormalization over our horseshoe, and then it descends all the way down. So therefore, it prevents super exponential divergence. Okay, and last, what I wanted to say is that everything above can be combined. Well, they are already in the near-degenerate regime. So in particular, it does imply the MLC for all real. Okay, so probably wine is getting warmer, so let me stop here.